Hi, folks. So the topic of this particular lecture is drawing free body diagrams and also some steps that we should take in every single problem that we have that has forces in it. Now, I say every single problem, but there's always some examples to any rule, right? Um, so first off, in drawing free body diagrams, what we want to do is we want to think about our object, maybe do a little sketch of our object, and then locate all points of contact between our object that we're interested in and the outside world. So for instance, if it were me sitting in this chair, then I would think about well, the contact that I'm making with the chair, and that's probably about it. Um, let's see, what else? From there, what we're going to do is we're going to do a separate kind of sketch which just represents our object as a dot. And then we're going to draw and label all our long range forces, which in this class is just weight, gravity. And then we're going to turn to the contact forces and look at all those points of contact between our object and the outside world and draw and label vectors for all of our different forces from those points of contact. And sometimes our points of contact may have two forces. For instance, if we've got a point of contact between two surfaces, then I might have a normal force and a frictional force as well. So let's see here. Let's see some examples. The first one says, draw a free body diagram of a ball flying through the air. Okay, so we can picture a ball flying through the air. Maybe it's got some velocity this way. I don't know. It doesn't really matter. Because all we want to do is just think about its free body diagram. It says to neglect air resistance. So if I think about the points of contact between the ball and the outside world, well, there really aren't any. And as a result, I only have one force that's acting on this ball. It's the weight force that Earth exerts on the ball. Okay. And that's it for a free body diagram. All right, on to the next one. This says draw a free body diagram of a skydiver that has reached terminal velocity. Okay, so we can picture our skydiver. There we go. Boom. Okay, so there's a skydiver. He's falling down at some terminal velocity. Okay, so falling down at some speed v. And now we can ask ourselves, well, what is it that terminal velocity means? Oh, that's his maximum velocity. So he's not accelerating anymore. What's keeping him from accelerating? Well, it's actually all this air right there is actually pushing upwards on his body. So there's some air resistance, some drag on this particular object that we're interested in. All right, so let's draw our free body diagram. We've got our dot. We've got a downwards force again that's caused by gravity. That's our weight force of Earth on our little dude, Earth on dude. And then we've got an upwards force due to air resistance. And we can call that air resistance, or we can call that drag. And I think we call that drag. And then we need to think about, well, what is the size of that drag vector in comparison to the size of our weight vector? And because of the fact that this guy has reached terminal velocity and his acceleration now is 0, that drag vector should be the exact same length as my weight vector, and that's drag due to air acting on my dude. Notice there that the second subscript is always the the object that I'm drawing the free body diagram for. All right, so let's look at another one. We've got a free body diagram of a car on a flat road that is applying the brakes. So we can draw our little car here. Okay, it's on a road. Let's see, it's moving with some speed. We'll put the speed to the right because why not? Let's see, it's applying the brakes. Let's see, where's our point of contact? It's right there between the tires and the road. All right, so let's start drawing our free body diagram. We've got our one long range force. That's our weight force, weight of Earth acting on car. And then what's holding the car up? What's keeping the car from passing through the road? Well, that's a normal force. And that normal force had better be the same length as my weight force in this case, because those are my only two forces acting in the y direction, and they had better balance out, or else the car is going to lift off the road or it's going to sink into the road. And you guys know that physically neither one of those things happen. And the other forces I have is the force that apparently it says the car is applying its brakes. This car is slowing down. Okay, so there's got to be a force to the left that's causing this car to slow down. And now we can think about what that force is. Well, the force has to be due to the contact between the road and the car. And it's a force that's slowing the car down. And the only thing that I can think of that would cause that would be a frictional force between the road and the car. By the way, if you guys are screaming at me right now because I mislabeled the normal force, yeah, you're absolutely right. I sure did, because it's not the earth that belongs there. It's the road. That's a contact force that's caused by the road acting on the car, not the earth acting on the car. All right. But now I think I'm all good there. Okay, so let's look what else we have. Okay. So these are the steps that we're going to take for force problems. Every single time we've got a problem that involves forces. We draw a free body diagram, just like I showed you guys in the last three examples. We define X and Y directions. This is nothing new to us. We did this with kinematics. We break our forces into X and Y components. Again, nothing new to us. We did the same kind of thing when we were dealing with 2D motion. And now we apply Newton's second law in the X and Y directions. So these are the steps that we're going to take in the vast majority of the problems that involve forces, definitely for this chapter, and probably for chapters to come as well. All right, that concludes this. So I will go ahead and see if I can't get this shut down. I will see you guys in class.